Okay, hello everyone, and welcome to the next talk in the Reality of Net Zero seminar series. My name is Mike Kendall. I'm the head of the Department of Earth Sciences here at the University of Oxford, and I'm a geophysicist, and I'm also director of the newly found program called Oxford Earth. And later in my talk, I'll explain what Oxford Earth is. Just a reminder to put questions in the chat, and we'll leave lots of time at the end to go through Q&A. But let me just move forward here. So the title of my talk is, as you can see here, Equitable Access to Natural Resources Needed to Achieve Net Zero. And what this is really getting at is we talk a lot about net zero and the need for renewables and the technology that's required, but we spend little time actually talking about where we're going to actually get the resources to achieve this. And I want to go into this in a bit more detail and describe some of the kind of new sort of game-changing ideas that people are considering right now. Just to set the context, this is a infographic that was put together by McKinsey a few years ago, but it really highlights some of the challenges here. If you look carefully at this plot across the top, across the x-axis, we have different technologies that are needed to get to a low carbon future or a net zero future. And these are predictable things like geothermal, hydro, nuclear, bioenergy, electricity networks, concentrated solar, hydrogen, wind power, solar voltaics, electric vehicles. And then if you look down the vertical axis, it shows the minerals that are needed in those different technologies. And steel's at the top, copper, and you go through a lot of familiar ones, and then ones that may be less familiar to people, like tellurium or cadmium, for example. But what you'll see is, for starters, steel is needed in all these technologies. There's a big demand for steel. And steel has its own challenges because currently we still conventionally use coking coal to produce steel. So even though we're producing something that's a renewable energy, for example, hydro, we still need a lot of steel. The other one that shows up a lot is copper. And just to give you an idea of copper demand, as we move forward here, this graph on the left shows the copper demand in different technologies, for example, building, industrial, as we move from 2015 through to 2100. And essentially, the amount of copper we're going to need by 2050 is almost going to triple. And to put that another way, is we need more copper in the next 25 years than we've ever consumed as human beings. So there's some real challenges here on how we're going to find the natural resources that we need for these new technologies. Others, like electric vehicles on the far right, you can see there's a whole host of exotic and less exotic critical metals that are needed to achieve that. Another category of elements, critical metals, that is becoming more and more of an issue right now are the rare earth elements. And these are very versatile, interesting group of elements. They really drive up performance in devices. One good example is magnets needed in wind turbines. You can make much smaller turbines to have very efficient wind electricity generation. And there's light elements, light rare earth elements, which are in orange here, and heavy rare earth elements. And they're used in not just wind turbines, electric vehicles, the medical industry, a whole range of things. Our mobile phones, our smartphones really rely heavily on this. And the interesting challenge with rare earths, again, is that the demand is just soaring. This plot here shows the demand from 2010 to 2035, and you can see we're like more than tripling the need. And there's a whole range of applications. The interesting thing about rare earths is there's a large geopolitical element. And this diagram here on the right shows where rare earth elements are mined. Then there's a separation. You mine them, then they need to be processed through separation, and then a refining stage. And really, one country dominates this, and that's China. When you look at 90% of the rare earths are refined in China, and 70% are mined there. And it's done in such a way that's environmentally quite quite harmful. It's a harmful, environmentally polluting process. And so there's some controversy over really how do we sustainably produce rare earths. And what you can see on this diagram on the top right is the demand again is quadrupling by 2040. And so these are really existential challenges that we have to face going forward with providing the resources that we need for net zero. This is another diagram. This is sort of shows the critical metals that are needed for the energy transition, and this was developed for the EU. And again, on the right, you can see the technology, electronic vehicles, solar, photovoltaics, electrolyzers, wind turbines, batteries, and then just basic cables and infrastructure. And then you can see the metals that are predominantly needed in those technologies in the middle column, sort of copper, silver, silicon. You get down to the rare earths, neodymium, praseodymium, dysprosium. And you can see the connection. But then where it gets more interesting is you look at what countries are providing those metals. So we got China as a very big producer, South Africa, Australia, the Democratic Republic of Congo, Russia, United States. And what's interesting about this list is there's not a single European country on this list. And whilst we have this increased demand and we need this security of supply, we're actually really dependent on other countries, other providers. And as recent events have shown us, if a country falls out of favor, is no longer open for business, then this can actually put a real strain on this demand. So we need, really looking forward a diversity of sources, and we need to have some sort of sustainability in the recovery of these elements. Okay. So this brings up issues of geopolitical expedience. Obviously, there's an enhanced, even more acute need to improve recycling of elements. Some elements are very well suited to recycling, like copper, aluminium. Others, like neodymium, it's more difficult. We need to be looking at new green technologies to provide these resources. And really what we're looking at is really disruptive technologies, disruptive raw materials recoveries. And that I'm going to talk to you a little bit about some of the ideas in this area. So there's some real key challenges we're facing. How do we supply these resources to a growing and energy-hungry population? That's a very acute need at this stage. But how do we do this in an environmentally responsible way? Historically, we've not done this in the most environmentally responsible way, and we really don't want to repeat the errors of the past. And how do we do this in an equitable way? I mean, it's fine for us here in the UK to say we're doing well with our renewables, but that's at a deleterious consequence to a country that's actually providing those resources. And then how do we manage a quickly changing geopolitical landscape? And so these are key challenges facing us as we move forward. I think what's encouraging, though, is that it's a very humans are very innovative. There's lots of emerging new technologies, and I think there's lots of reasons to be optimistic that we can actually navigate this change. And this, as a neuroscientist, is very positive because I see this as our science is providing the resources that we need in these changes. So you've already heard in previous seminars in this series about about some of the programs in Oxford, like Oxford Net Zero. Next week, Paul Shearing will be talking to you from the ZERO Institute. And there's a whole series of things going on that really sort of link up initiatives around net zero and the environment. So the Oxford Net Zero program, really looking at how do we reach net zero, what is net zero, what's needed in terms of governance, regulation. The ZERO Institute, looking at zero carbon energy systems. There's a new program in sustainable chemistry, concentrating a lot on photovoltaics. And then there's lots of training elements also at the same time, centers for doctoral training and use of AI in earth problems. And what I'm going to talk to you about now is a new initiative, which is called Oxford Earth. It sits in the bottom of this, what I call a Venn diamond, which links all these things together. And so what Oxford Earth stands for is equitable access to sustainable resources for a thriving habitat. And really the question is, how do we sustainably resource our transition to a net zero world? And to do that, there's a real recognition that working as we've done in the past, just in a single discipline, is not the way forward. And so this is a cross-departmental program, 9 departments across 2 divisions, which would be faculties and other universities. And we're looking at a whole range of issues from waste management, geothermal, biomaterials, CO2 storage, critical gases like hydrogen and helium, critical metals. And as I said, to really be successful in this, we need a cross-disciplinary approach. So we want to look at not only, how do we actually find these resources, get them out of the ground, process them, but we need to look at the ethical implications, the policy implications, social implications, and also aspects like law and regulatory things. I think stakeholder engagement is crucial, how we work with industry, how we work with governments, how we work with NGOs, and really how we interface with the public is kind of crucial on this going forward. And so here's some of the key research themes. A lot of this we like to sort of simply describe as the mine of the future, where we've got a really good ecosystem on the surface, above, in an environmentally friendly and sustainable approaching to mining resources at depth. And I'll go into some of the approaches to that as I give you some examples. But some of the key themes here are really, how do we get at these critical metals that I've already discussed: copper, lithium, rare earths. What about critical gases? Hydrogen is going to be a key component in the energy transition. And what's often associated with hydrogen is helium, and people don't realize it, but actually there's quite a chronic shortage of helium in the world, and it's needed in not so much for net zero, but a lot in medical uses, for example. There's a whole theme on the use of microbial metal recovery and reuse, waste recycling, and I'll give you an example of that in a minute. Then we want to really, better understand and better mitigate environmental impact. So looking at things like bioremediation, waste treatment, nature-based solutions, for example, in terms of recovery. And obviously in this context, we want to avoid hazards too. And then looking at the economy, really looking at circular economy, supply chain analysis, recycling, repurposing. How can we do a better job in that area? And as I've already said, history, reflecting on the history and the ethics is really important in this. And I think one of the most important things that we need to consider is social license, is getting people to understand and accept, the changes that are needed. And then finally, policy and regulation. So this is very ambitious. This is to start a 5-year program that will sustain itself beyond that, and it's bringing together all these different elements. So I'll give you some examples of current progress in a few areas. The first one is microbial mineral bioproduction. And this is really led by 2 of my colleagues, Professor Julie Cosmides in Earth Sciences and Professor Harrison Steele in the Department of Engineering. And Julie wrote a really nice opinion piece recently entitled, "Will Tomorrow's Mineral Materials Be Grown?" And it's a really fascinating idea that how we can use microbes in manufacturing. We already do to a large extent in food, pharmaceuticals, bulk chemicals, biofuels, polymers, but there's some really exciting potential for using microbes in the production of minerals. The advantage is that this is a very energy efficient approach with reduced carbon emissions, reduced waste. It leads to very, ideas of circularity and recycling. And it's firmly in the area of bioengineering and synthetic biology, which is a rapidly growing area right now. So microbial minerals incorporate elements across most of the periodic table, and people don't generally realize that. These are some exotic microbes shown under thin section here that are very good at fixing things like sulfur, iron, manganese, copper, for example. And microbes can be tricked or used and manipulated to concentrate and mineralize elements, even when those minerals are only available in trace concentrations. And so what this means is we can use biomining of metals from waste resources or bioremediation of contaminants. And it's a really exciting new growth area. And I'll just finish this example by showing an example of one of the things that Julie and Harrison are looking at, is basically using microbes to help manipulate material manufacturing of particular technological applications. And so in this example, this particular microbe is fed nitrate, carbon dioxide, and H2S, and can be used to actually grow lithium silicon batteries, which is a new technology in battery. I mean, it's at the laboratory scale right now, and the devil's in the detail. The challenge will be how do we scale this up to commercial operations. Another example is microbes can be used to secrete cemented silica. So in a sense, you grow bricks without the use of cement, and again, a low carbon technology. Then what I'm going to talk to you in a bit more detail is about the idea of co-recovery of metals and geothermal energy. And this leads into a whole area what sometimes is called green mining. And this is led by John Blundy and myself and others in earth sciences, and Dermot O'Hare in chemistry, and others across the university. And this idea is attracting a lot of attention. So here's from the Financial Times, the headline: "The next critical mineral source could be a volcanic soup." And I'll go into a bit more detail about what that means and what the approach is. So if you step back and think back to sort of your GCSE or A-level geography or geology, if you did A-level geology, the Earth is the ultimate recycler. It produces new plates, it destroys plates, plates slide past each other. And the whole process of plate tectonics, when two plates collide, one plate subducts under the other, that's shown here, and it brings fluids from the surface, seawater and other fluids down. And as these fluids heat and warm, they melt the rock around it, and then they rise, because they're buoyant, up towards the surface. And they essentially produce volcanoes or lines of volcanoes. And you see this in the Andes, for example, or across Japan. And so there's a way of concentrating the critical metals. And if these fluids are high in, are very saline and they're hot, they will concentrate critical metals, rare earth elements, things like that. And so essentially, this is the way the Earth distills these critical elements that we need in these volcanic systems. So if you think about what conventional mining is doing for metals, so here's an example of one of the world's largest copper mines. It's called Cerro Colorado in Chile. And this is a huge hole in the ground that is, this rock is dug up. About 99% of the rock is thrown away, and less than 1% is used to get the copper out. So it's a really energy intense operation with a huge environmental impact, as you can see here. But essentially what you're looking at here is the heart of an old extinct volcano. So it was an active volcano millions of years ago, and it's long since cooled. When trying to find these things is actually quite difficult. There's sort of on the order of a handful of mines across the world that produce most of the copper that we currently consume. And so that's the challenge right now with conventional mining, is to find more of these types of mines. But the other approach that we're taking and thinking about is saying, well, why go to an old extinct volcano? Why not go to an active volcano? So here on the right is a picture of Mount Etna in Italy. And on the left, what is shown are is the gas flux. In other words, what's coming out of the smokestack at the top of Etna here in terms of elements. And you can see there's things like sulfur and chlorine, which are less interesting. But if you go to the far right, there's over 10,000 kilograms of copper emitted each day from Mount Etna. And that's getting close to how much copper is mined each day on the planet. And so these volcanic gases are carrying a real diverse portfolio of metals in huge abundance. And we know from the way volcanoes work that if this much is coming out the top, there's got to be much more retained and trapped in condensed fluids deep underneath these systems. Volcanoes are easy to find. Anybody using Google Earth can find them. There's over 2,000 degassing volcanoes worldwide. And so this raises the really interesting question of, can this resource be accessed economically? And John Blundy and co-workers recently wrote a paper that's essentially a blueprint of how to do this, looking at what has to be considered. And it's interesting, each volcano has its own signature, and each environment the volcanoes are in have, some will be better for rare earth, some will be better for copper. And it's understanding that's quite an interesting bit of research right now. In the center of this figure here shows some of the approaches that we can take for getting critical metals from these geothermal volcanic systems. And this is a really disruptive strategy for metal recovery. It's really thinking of things in quite a different way. If you look at this figure in the middle here, in the most shallow part, we've got shallow boiling water, upflow of water from deeper in the earth. As you go a bit deeper, getting over 200, close to 300 degrees, you get into the conventional geothermal reservoirs, which are now used quite routinely for generating electricity. And if you go a little bit deeper, you get into, sort of getting close to above 400 degrees, depths of about 5 kilometers, you get supercritical fluids. And these supercritical fluids, if they're saline, if they're salty, they're really good at latching on to minerals, metals that are coming off the magmatic bodies below. So the magmatic fluids will get concentrated in this area. And so the approaches for extracting metals from this sort of system there's a number that can be considered. Item one here is just direct metal capture from hot fluids. This is a picture from the Salton Sea where lithium is being produced from hot fluids directly. As these fluids are rich in metals, they will scale up the piping that brings the fluids to the surface. And this is a very common problem in geothermal energy. And geothermal companies generally put down harsh fluids such as acids to try and get rid of these metals. So they deliberately try to descale the pipes to keep the fluids moving for geothermal energy. But this picture here, what you're seeing is scaling on the inside of a pipe. And in many cases, the scale, the ore in this is as good, if not better, than any producing mine in the world. So a very exciting potential approach. Another approach, which is called number 3, is take an existing geothermal power plant that's producing fluids and then take some of the excess fluid and extract minerals that could be useful from that. So there's a company in New Zealand, for example, that takes colloidal silica out of the waste fluid in the geothermal plant. And it doesn't sound that exciting, but actually this silica is used a lot in creams and pharmaceuticals. And so it adds an extra revenue stream to the geothermal electricity stream. And then the fourth approach, which is something that we've been working a lot on, is this idea of, can you inject things into these rocks that have been formed in these volcanic systems to help encourage more of the critical metals that you might be interested in out of this system. And you can do this in sort of a clever way when, this week you may need copper, so you might enhance copper out. Next week it might be tellurium or something else. So you can start to think about how one preferentially extracts in these environments. So this all sounds a bit sort of hypothetical, but actually there are examples of where this has been done. So here's a picture from the Kokonda power plant in Japan. It's a geothermal power plant. Japan, as with many countries, has a hard time with geothermal energy because it's still much cheaper to produce power using a diesel power station or a gas power station than a geothermal power station. And so in 1995, they drilled almost 4 kilometers in depth in this area, encountered fluids of temperatures 510 degrees. And that's because they're really interested in supercritical geothermal to try and get more electricity for the capital expenditure. But what they also, by analyzing the fluids from this geothermal power plant, saw again, the whole periodic table of different minerals. And so They're organized from left to right here from in terms of value. So gold is a significant amount of gold in these fluids, but also silver, copper, lithium. Basically, by taking into account the market worth of those minerals, all of a sudden, if you could extract them and get revenue from that, it makes your geothermal power plant with a co-recovery of critical metals very competitive, if not more competitive than gas-powered electricity. So, there is a proof of concept that we can actually drill to these sort of depths in these sort of environments and see the minerals in the fluids. So one of the very first projects of OxEARTH is something called RESET, and this is reframing metal mining for a sustainable energy transition. It's funded by the Oxford Martin School, and it really focuses on the island of Montserrat. Montserrat was a very thriving Caribbean island on the verge of independence, and then Hurricane Hugo hit in 1989, destroyed the tourism industry. 90% of the infrastructure had to be rebuilt. And then in 1995, the Soufriere Hills volcano, shown in the lower left here, started erupting, and it went into a sustained period of eruption that wiped out the southern part of the island, the capital and stuff. So it's had a devastating effect on the island. The population went from almost 14,000 people down to its lowest about 2, and it's now about 4. At the same time, about 10 years ago, 3 geothermal test wells were drilled and showed that there was really good geothermal potential, very successful wells. But again, Montserrat's struggling with the cost of the capex, the infrastructure to actually produce the geothermal energy. And so what this research program is really looking at is how is there potential to look at the co-recovery of metals and geothermal energy? And again, as I said in the beginning, this is only going to be successful by bringing together a whole range of different disciplines. One of the most important ones is actually really engaging with the people of the island. Do they want to go to geothermal energy? Do they want the idea of having a small mining operation on the island, that sort of thing? And it really looks at these interconnected issues across broad themes of resources, rights, risks, and resilience. So I won't go through, there's a lot of people involved, but people from earth sciences, chemistry, here in geography at the Smith School, economics, history, law. And then we have very good connections with the Montserrat Volcano Observatory, the government of Montserrat, and the Foreign and Commonwealth Development Office. And then advisors from Montserrat and the Caribbean also in this program. And it's divided into sort of 4 kind of obvious work packages. One, how do we optimize our exploration of the potential geothermal fluids and the critical metal endowed fluids. Work package 2 really looks at how do we assess that metal endowment and the recovery. 3 is looking at the economic and regulatory framework. And 4, how do we equitably extract this energy and these minerals and with social license. And so what I do is I'm a geophysicist, so I'm the one that helps look for these resources. It's great fun. We put out seismometers across the island, even into the exclusion zone. It's a tropical, dense vegetation, so one of the challenges when we come back, we have to actually find the instruments. There on the right, so that's using a metal detector. At the same time, partners from Montserrat, Trinidad, and University of Alberta in Canada are doing magnetotelluric surveys, which look at conductivity anomalies. And we end up with getting images of what the subsurface is, just like medical imaging. We use earthquakes as sources, or we use natural background electromagnetic signals from things like lightning strikes or solar radiation interacting with the ionosphere. And we get these very high detailed, high resolution images of what the subsurface looks like. And that's one of the things we're working on right now. Then we can look at the rocks and the fluids that are from expressed at the surface or in the boreholes, or in things in the upper right here is something called hot water ponds, areas where hot water comes to the surface. And we can assess what sort of minerals, what sort of metals are in the system. And here's fluid sampling from one of the boreholes. And some preliminary results, which are quite exciting, is that we are seeing some high concentrations of some of the critical metals, not in the water and not so much in the rock, but in the sludge, the stuff that sort of essentially scales out as the fluid's arriving. That means that it's tapping some of the magmatic fluids that we're interested in. Looking at the regulatory framework, obviously you can't just start mining a particular mineral without having the right framework. And there's a lot of work going into understanding what Montserrat's energy policy is, what its Minerals Act is. But the island is very clearly committed to a sustainable development program. And then finally, an ethnographic study looking at, what do the people that live there feel about this sort of work? What do they feel about geothermal energy? And generally, there's widespread support, but a lot of work is going on into just better understanding what's thought. There's definitely a fatigue over the volcano continually erupting, and there's a definite desire to get a political and economic framework that works for geothermal and get it underway. Lots of public and stakeholder engagement. There's a new premier of the island. We've met with the governor. This is us with Graham Ryan from the Montserrat Volcano Observatory. I was on the public radio there. We visited local schools to talk to people, to get ideas, tell them the type of research we're doing. It's been an incredibly rewarding project, and already we're seeing some interesting ideas about how to move forward. So just to finish in this area, I'm going to just mention a couple of the spin-out companies that are really coming out of Oxford in this area, and they're in some interesting. One is called Ascension, and really Ascension's mission is to harness metal richness and the natural power of volcanic systems to recover critical metals in a responsible, efficient, and sustainable way. And here's one of the first examples that Ascension's involved with. It's with the university and a drilling company, and it's funded through Innovate UK, and it's got a geophysics component and a geochemistry component, and then a modeling component. And it's really looking at, it's concentrated on the island of Ascension, which lent its name to the company, as a UK overseas territory with potential for metal extraction. Another company is called Snowfox Discovery. This was spin out from, started by Chris Ballantyne and Mike Daly of the Department of Earth Sciences, and this is really looking at natural hydrogen. So you hear a lot about hydrogen in the press, and there's different colors of hydrogen which make it slightly confusing. So gray hydrogen is really, you're using hydrocarbons to produce hydrogen. So it's not really a benefit in that sense. It's producing what's shown on the y-axis here is carbon intensity. It's a very carbon intensive process. Blue hydrogen is again using hydrocarbons, and the idea is you'll capture some of the carbon. Again, it's quite an intense operation. Green hydrogen, you're using renewable electricity to produce the hydrogen from water, for example. And so it's getting better. But the really sometimes what's called gold hydrogen or natural hydrogen is actually finding hydrogen in situ in the Earth's crust, just as we find oil and gas. By moving towards natural hydrogen, it is estimated that 50% of future hydrogen demand, the switch from grid concentrated green hydrogen would save 95 gigatons of CO2. So zero carbon emission, low emissions in extraction, and limited broader impact. And this is what Snowfox is really concentrating on, is this untapped resource potential. And again, some of the headlines here has been picked up in the press, and it's quite exciting potential in this area. So just to sum things up, I mean, I've covered a lot of different areas, and I've certainly not been exhaustive in some of the ideas and some of the things we're thinking about. But really, the way forward is I see it, is the research in the earth sciences will provide solutions to how we're going to sustain and how we're going to provide the resources we need for net zero. And it's not just the resources that we need, it's also what do we do with the waste storage, so for example, radioactive waste or the geologic storage of CO2. I personally think working with industry is crucial. This is how we're going to scale these things up, how it's going to be economically viable. What all this means is, it does not negate the need to reduce, reuse, and recycle. We still need to do a lot better, be a lot more efficient in how we use the resources that we have. Hopefully convince you that the ideas of co-recovery of geothermal energy and critical metals is very exciting. Equally, I didn't go into it very much, but hydrogen and helium exploration is an area of huge interest and huge growth right now. I see a lot of potential in bioremediation, biomining. I showed you an example of how lithium sulfur batteries can be grown using microbes. I didn't talk about sort of waste storage, but carbon capture and storage is certainly a key component in achieving net zero. And I think the really crucial thing is social license. And the more and more I work on this, the more I realize that actually without social license, we're not going to go anywhere. So we neglect our sort of public communication of science at our peril. And a really important objective in all of this is that, in us achieving net zero in one part of the world does not lead to deleterious consequences in another part of the world. And I think that's a really important thing as we move forward. I've just put on this infographic here from NREL in the US, the circular economy for energy materials, and it's got everything from resource extraction through to material production, design, manufacturing, recovery, then recycling. And the different programs across Oxford Net Zero sort of sits above all this, encompassing it, but then OxEARTH, the ZERO Institute, Sustainable Chemistry play critical roles in these. And I think it's interesting looking forward in that there is no one silver bullet. We have to address all these elements of this circular economy for energy materials, and that's sort of where we're heading. So just to finish, climate change is obviously one of our most pressing societal issues, and reducing our dependency on fossil fuels is a key challenge. But I'm optimistic in that humans are great innovators, and we're now more than ever seeing innovations in a wide range of areas. And I'm sure in 10, 20 years, there'll be technologies we haven't even thought of this time. It's exciting for me as a geoscientist, a geophysicist. The field of earth sciences is actually providing solutions. It's great to teach students about these ideas because there's a sense you can actually make a difference and address these challenges. And finally, I think interdisciplinarity is in collaboration is really a key as we move forward in this area. And so I'll finish by just saying an advertisement for next week is Paul Shearing from the ZERO Institute. And you can see recordings of previous seminars in this series at this address here, netzero.climate. And my presentation just finished. So I'll take questions now. Thank you. I'll just move to the Q&A button. Okay. So the first question is, the Mount Etna example is truly remarkable, but what are your thoughts on the dangers of creating incentives to destroy beautiful, active volcanic landscapes for mining? Given the recent perceived attack on national parks in the US, we could end up with people trying to bulldoze Yellowstone for critical metals. Yeah, so that's a really good question. And the key, it goes back to that image I showed you of the mine of the future, where there's a borehole that is drilling into the fluids, and there's another borehole that's extracting them. So if this is done as I described, the surface footprint of what you're looking at would be something about the size of this room encasing the injection borehole, and something similar for the extraction borehole. So it would be smaller probably smaller footprint than a geothermal power plant. So that's the beauty of the approach, is there's no more excavating or digging up huge tracts of ground. It's really trying to do things in situ in a environmentally sustainable and responsible way. There's a question here that says, many schools experience a decline in enrollments for sciences, and in recent years, several geoscience departments in Western universities have been discontinued or related disciplines have been phased out. What are your thoughts on this trend? And this, I'm glad somebody asked this question, because it is very perplexing. There's more demand right now for our scientists, geologists, geophysicists, geochemists than ever. The demand is rising, and yet student interest numbers are declining. And it's a real paradox that we need people trained in these areas, and yet we're seeing reduced numbers of interest. And I think the way to address that is first public information, public communication, getting across really how the skills in the earth sciences are needed in these technologies, just as they have been for the previous decades in mining and oil and gas. It's a new industry now. And then also, I think it's really important that we sort of interface with government and education authorities in that. Certainly in the UK, one of the challenges is that students in high school really don't get exposure to what geology, geophysics is about. It sort of falls between physics for the geophysics side, chemistry for the geochemistry side, and geography for the more geology side. So I think we as educators need to do more work in showing the importance in this area. But thank you for that question. It's good. Another question is, I'm curious about the scalability of biomining. Can it replace traditional mining, or will it capture a larger share of the industry? My honest answer is I don't know. I think it's highly unlikely that it would replace traditional mining. And to what degree it can be scaled up is to be seen. I think where it is really exciting is, near where in Oxford here, we have huge old quarries filled with ash waste from power plants that we know are full of valuable metals and stuff. And so as a start, if we can do a much better job of cleaning up that's going to be a very important contribution to the resources we need, but also a very important environmental remediation step. But to what degree this will, I don't think it would ever be the sole thing. It's never going to replace mining per se, but we may hopefully not need traditional mining where we dig a big hole with some of these other ideas of looking for fluids in other settings also. Comment here says that net zero cannot be achieved through equitable access to resources. It can be initiated through sustainable resource use and resource mobilization. Justification as follows. Access to resources is uneven and uncertain, as not all countries across the geographies are on the same page of resource availability, so access becomes a persistent problem for the countries seeking it. My question is how to infuse ease of access with reducing disparities in resource allocation. And that's exactly what OxEARTH is trying to do. I mean, this sort of uneven representation of minerals by geography is a long-standing problem. So I mean, you just need to look at the Democratic Republic of Congo, produces many minerals that go in everybody's mobile phone, and the country isn't really benefiting in an obvious way from that. One of the nice approaches or thoughts about mining volcanic systems and volcanic fluids, geofluids, is they are much more prevalent worldwide. I mean, even the UK has volcanoes in overseas territories. And so that, rather than trying to find a few copper mines in Chile, Australia, Mongolia, Canada, we can look more widely. But I think the point is really good in that we need to be much more equitable in and much more responsible in how we extract resources globally. More access to resources, more shall be the emissions. So net zero can be approachable if we cap the use of resources for emission reductions rather than cap and trade. It's a systematic option for carbon allowance and allocation. Your take on this? I'm not quite sure what you're getting at here. We can't. The idea is to exploit or to find and produce resources in a zero carbon approach. Okay, so for example, if you can co-locate a geothermal power plant extracting critical metals, the power from the geothermal power plant would power the whole thing, and then you can do it in a carbon neutral way. And I think approaches like that are more, what we need to strive for. So I'm not sure I've actually answered the question very well, but that my take is that we need to, whatever we do going forward has to be certainly low carbon in the approach. Also, the future for net zero, if it has stand up and high, should not to mine for future, but recover resources, whatever is available, and use and bring it back to the life cycle. I agree completely. We should be recycling, reusing, looking at circular economy completely. But given the demand right now, there's no way we can provide enough copper just by simply recycling and reusing. And I think that's really important, that we make sure that we do not neglect recycling and reusing and being more efficient in how we do things. That's crucial. But sadly, we do need more of most of the critical metals that I've described. What do you think the timelines may be for scaling of any of these new methods of acquiring metals? Well, I think that's so scaling up is an interesting question, and it depends very much on where you're talking about doing it. In this country, in the UK, it's actually very difficult to do anything in terms of new technology, so-called NIMBYism, or the idea of doing stuff here. Really, it's difficult. And it's a shame, because we seem quite comfortable to be able to take resources from other countries, but at the same time, don't really want to see or have any access to that. Other countries like China, for example, are incredibly quick at scaling up. When an idea is good, and sometimes that's done at the detriment of other things, environmental license, that sort of thing. And so it has to, we need to scale as quickly as possible, but in such a way where due respect is paid to the people that it's influencing and the environment that it's influencing. I think with current political things right now, I think you'll see things starting to scale much more quickly. And actually these ideas, so microbial production of metals, there's less concerns about environmental impact, and that technology should move forward very quickly. The idea of co-recovery of metals and geothermal, again, it should be very quickly. One point that I hadn't really talked about was about, you can get the fluid out with the metals in it, but then you've still got to extract the metals from the fluid. And there's a lot of research being done here in Oxford and other places on how to do it. It's basically a chemistry and materials problem. But I think that technology could scale very quickly, sort of as in the next 5 to 10 years. Are there critical shortages now in any of the materials, i.e. something is so limited that it's preventing renewable energy development that could otherwise happen? Yeah, the honest answer is I don't know. If you'd asked people about 10 years ago, they'd have said, well, lithium's a big problem, big shortage. But actually now, lithium is less in a scarcity. In fact, most producing oil wells produce more water than oil and gas, and a lot of that water has lithium in it, as an example. There's some exotic minerals that are needed in other technologies like fusion, for example, which are quite hard to come across. So as fusion scales up, that actually could be a limiting factor. So there's an isotope of lithium, lithium-6, which is actually very difficult to produce and actually very nasty environmentally in how it's currently produced. So that could have impacts in that technology. What policy changes can be made to integrate sustainable metal recovery? I think that's a good question in terms of policy changes. One policy change I think would be quite good right away is that there's a tendency for companies to say, I am a lithium company or I am a copper company. And so they produce, so in lithium, they'll produce fluids, but there could be other things in the liquids that are valuable. Scandium, for example, that company's just not interested in. And we know from traditional mining, there's big slag heaps full of all sorts of interesting minerals and metals. And those indeed are being now re-looked at and reused. And so I think some policy that says you have to be more efficient in what you do and what you use would be helpful as a start. I think, yeah, it's some sort of assessment of the resources, more full assessment of the resources that you have at hand would be very good. Given that mining companies often do not directly recycle minerals and that urban areas generate significant recyclable metallic waste, could integrating recycled materials into existing mining foundry processes, as in iron and copper, enhance their efficiency? I mean, to me, that sounds like a really good idea. I'm not enough of an expert in that area to know whether or not that's feasible, but that sounds like a logical thing to consider. Okay, I think we're finished Q&A, unless I'm misreading something. So thank you, everyone, for really good questions and thought-provoking questions. And again, I'd encourage you to look at the previous seminars in this series, which are online, and also encourage you to attend next week's seminar. So thank you again for your attention. Thank you.